All right. Well, thank you to the exoVAST team for having me. Great talk, Joe. Thanks for the introduction, Michael. Excited to see the VAST series continue, and especially this exoplanet specific weeks, and excited to be one of the first talks on exoplanet specific weeks with my code MAGRATHEA. MAGRATHEA is a planet interior code which has been hosted on EMAC now for the year since it's been published. EMAC has been a great tool to publicize the code and share it with other people. And I developed the code along with Chenliang Huang at the University of Nevada, Las Vegas. And Chenliang was a postdoc and I was a PhD student here in Las Vegas. Chenliang's now faculty or staff at the Shanghai Observatory. And we were advised by Jason Steffen here at UNLV. Now we're both moving on, but we're both developing MAGRATHEA still while working on some other projects. I'm now at the Astrophysics Research Center of the Open University of Israel, advised by Alona Bazan. So I'll be talking about our code MAGRATHEA. So I think we've probably all been there. We've got a planet. We've got maybe the mass and radius. Maybe we have some surface properties. Maybe we know something about the interior here in the solar system. And we've all wanted to just cut it right open and check that it's not cake and see what's inside of this planet. So that's a very funny little explanation of it. But our solution to this problem of figuring out what's inside of a planet is MAGRATHEA. So here's highlighting some aspects of the code. It's an open source planet interior platform. So although we have a default model, we've really tried to program it so you can build your own model for whatever type of planet you want to solve. We publicized it in Huang, Rice, and Steffen 2022. MAGRATHEA is the fantasy planet from Hitchhiker's Guide to the Galaxy where they build other planets. So it's not any weird astronomy acronym. It's just MAGRATHEA. It's written in C++. It uses shooting to a fitting point method. That's just to say it's wicked fast. It takes about 1 second to run a planet. Although I use it mostly for terrestrial planets, it's extensible. We can do sub-Neptunes with it, mini Neptunes, even up to Neptune. We just need to think about where these equations, if you provide the equation, we'll solve it. We want to think about where these equations should be used within these planets. And many of these parameter spaces, we don't have better equations for. And it's also transparent, which I'll talk about a lot in this talk. So just a quick explanation of a planet interior structure model. These have been used since 2004 with some of the first works listed down in the bottom for exoplanet science. Planet interior structure models generally are one-dimensional, spherically symmetric, fully differentiated shell models. So we solve in each one of these shells the equations of hydrostatic equilibrium. Here, including an isentropic temperature gradient is the default. We can do some other temperature gradients within that planet also. You put the total mass in each of these differentiated layers, and we get out the radius, the pressure, the density, and the temperature here, all with enclosed mass or with radii. And the problem or the interesting thing about planet interior structure model versus like a star structure model is equations of state. Is you have a lot of different compositions within your planets, and we need to know how all of these materials respond to pressure and temperature. So while some of the first models use just one composition for each of these differentiated layer, what you really want is a phase diagram within each layer. So what your mass you're inputting tells you which layer you're in, but then once you're inside a layer, the pressure and the temperature determine what composition and what equation of state you're using. So these are the default phase diagrams of MAGRATHEA for the core, mantle, hydrosphere, and we have an ideal gas atmosphere. We've got that hexagonal closed packed iron in the core along with liquid iron, these phases of magnesium silicates in the mantle along with silicate melt, and these high pressure ices along with liquid water in the hydrosphere. In this equation of states library, and these phase diagrams are ever expanding in the code. Focused on these equations of state, each one of these materials, we need measurements of how they respond to pressure and temperature, ideally laboratory measurements. And that's really what inspired MAGRATHEA for us, is we wanted to get in this interior game because downstairs in Las Vegas, we have a high pressure physics lab. And we wanted to take their materials they're crushing in diamond anvil cells and put them into planets. And we realized there was really no open source software in order to do this. So that was our motivation. And to do that, we have a lot of these imperial equations of state. So this is the Birch-Murnaghan third order equation of state. You can see the bulk modulus here, the reference volume, the derivative of the bulk modulus. These are all things high pressure physicists determine for their materials. Bulk modulus is the resistance to compression of the material, or 1 over the squishiness. And we have 6 different formulations for these equations of state. So all these different fitting formulas of how these materials respond to pressure, also how these materials respond to temperature. So this is a Debye thermal pressure determined by the Granissen parameter. And we have 3 different formulations for the temperature of these materials. So that was a super fast explanation of what MAGRATHEA does. I'm not as daring as Joe, so I'm not going to do a live demo. This talk will force me to put the tutorial. We have the paper describes the code. We also have a great description on our GitHub. I also developed a tutorial for Rocky Worlds Conference that I've been meaning to put on the GitHub. So this will force me to do that. But what I wanted to focus on in this talk is showing you a bunch of graphs. So a bunch of ways to visualize these outputs from MAGRATHEA, which will highlight different aspects of the code and hopefully inspire you to analyze an interior yourself and see how they're responding, or how these planets look in the inside. So this first graph, this is kind of summarizing all the things you get out of MAGRATHEA when you put a planet in. So the top is planet 1. This is a 1.1 Earth mass planet with a thick hydrosphere. It's got 0.3 Earth masses in the hydrosphere and the water, 0.4 in the mantle, and 0.4 in the core. While planet 2 is a more Earth-like planet. It's a 1 Earth mass planet with this 33% core and 67% mantle. Starting the mantle hot here. So this graph is pressure on the x-axis going inside to the right, and temperature increasing on the y-axis. The dots here are each of these solutions at adjustable step sizes of enclosed mass that MAGRATHEA solves for. So you can see the mass increasing from 0 inside all the way up to the planetary mass on the outside. And as the MAGRATHEA shoots for this solution, it follows the isentrope of temperature through these different compositions. So the top planet starts in water, goes through these high pressure ice phases, ice 6, ice 7, ice 10. We can put temperature discontinuities between the layers. So we see this temperature discontinuity in the Earth between the mantle and the core. So we want to be able to simulate those if you want them into your planet, or you can keep them all at thermal equilibrium and not put a discontinuity. But for these to demonstrate, I put a temperature discontinuity between the layers. So it jumps up into Bridgmanite, post-perovskite, this high pressure silicate, and into hexagonal closed pack in the core. While the Earth-like planet, instead of having that hydrosphere, has these lower pressure magnesium silicates, is forsterite, wosleyite, and ringwoodite, into the Bridgmanite, into the post-perovskite, into this HTP iron, and it even has a small layer of melt on top of that iron core. So that's a basic MAGRATHEA output. And with all of these materials, what we wanted to create is what we want to show is just how many parameters go into these works. So the top planet has 65 parameters from 8 different works, how these materials are responding to pressure and temperatures, and their phase and the transitions between the different materials. And the bottom has 48 parameters from 7 different works. So in MAGRATHEA, we created a library of all these planet materials and measurements for different materials. So we can recreate the planets from Siegert 2007 work, or you can use the most up-to-date physics and geology measurements of these materials. So this is a mass radius plot with some lines of isocomposition on it for 100% water planets, 100% mantle planets, and 100% core planets. And here we're just changing which material or which measurement for the material is the dominant one in each layer. So on the top is 5 different measurements of water ice. The purple line is if you don't include ice 10 in these planets, which some earlier works did not have measurements for ice 10. You can see that quickly creates planets up to 5% difference in radii. The mantle planets have some different measurements of Bridgmanite and post-perovskite. and the core has some different measurements for hexagonal close-packed iron that can create planets up to 2% difference, and 2 iron silicate alloys, which can create planets up to 5% difference if you're lightening that core with some silicate inside the core. I want to highlight here that we have new measurements from UNLV physicists. So in Wang Rice et al. 2021, we took some new measurements for ICE 7 and ICE 10 from UNLV physicists and modeled planets with them. And I also have a high school student adding equations of state to the code. So Sri is looking for college right now. He's applying, but he added all the materials from Stickfruit and Lithgow Bertoloni 2005, which is this massive table of mantle materials. He's added those all to the code. So this is a big library we have that you can easily swap in and out equations of state into your phase diagram, change your phase diagram around to see how this planet responds to these different measurements. And I just wanted to show this is the only code I'm going to show it. Then it's back to all graphs. So these are 2 different measurements of iron HCP, the transparent storage structure we have in the code. So this in the equation of state list.cpp. We've got 2 measurements, one from 2013 and one from 2017. 2013 was a experimental work, while 2017 was a compilation of some different works. And these both use different formulations for the equation of state. So this 0 parameter here, we have all these parameters tabulated in the paper and the GitHub. The first one uses a Hauseffel equation of state, while the bottom one uses a Binet equation of state. And you can see the bulk modulus here, equation 2, or parameter 2, differs by 100 GPa. So this is 100 gigapascals difference on how, in these formulations, this material responded to pressure in these 2 different works. So they often don't even overlap to 1 sigma, these experimental measurements. So back to the graphs, done with the code. All right, I've got like 8 graphs to show you for the rest of the time of just cool things you can make with MAGRATHEA. This is all of the small confirmed planets with under 10 Earth masses, with some cutoff for the temperature and some cutoff for the uncertainties, that have both masses and radii measured. And we've plotted curves of isocomposition on this bulk density plot with mass on the bottom. So these aren't independent measurements, but you can see these different groupings of iron-rich planets, mantle-rich planets, and water-rich planets, and even planets that require some atmosphere. So you can make these mass radius curves, provide a small document of masses and different and isocomposition, and MAGRATHEA will solve it in just a few minutes. One of my favorite things to make is ternary diagrams. So you can make a ternary diagram in the code in just an hour. This is the radii of 1 Earth mass planets. So with these 3 different components, mantle, water, and core, this is all the radii you can get for 3-layer differentiated planets of 1 Earth mass. So Earth is down here at 33% core and 67% mantle. You can see this blue is about 1 Earth radii. And then all the planets along this blue curve have the same mass and radii of Earth. So you can get, as you increase the core, you increase the water to keep that bulk density the same for the planet. And one thing I've done is now thinking about that line of constant mass and radii, we can make a composition finder. So for a given planet, we're going to translate this weird ternary diagram looking thing into a more normal plot. So we can think about a ternary diagram that the bottom axis is the core to mantle mass ratio. So as you swing one of these lines over, this dashed line, as you swing it over from one side of the bottom to the other side, we're going to define that as the RCMF. So the RCMF, the refractory core mass fraction, is a core divided by the core plus mantle. So you can think about it as the iron to silicate ratio, or the iron plus over the iron plus silicate, although the composition could be different. And then going up on a ternary is the water mass fraction, at least in this rotation. So the weight percent of water on the right plot is the y-axis, and there's no weird forbidden regions on this plot. All of these planets are possible. Here on the dashed line are all planets that have the same iron to silicate as the Earth under the water layer. So as you increase the water layer, then keeping the core to mantle ratio the same on that dashed line. So if we take a mass and radius of a planet, we can then solve for all the different planets that for 3-layer compositions that match that mass and radii. So here we have a composition finder in the code that you swing across refractory core mass fraction. And then the refractory core mass fraction gives you your core and your mantle masses. And then you shoot for the water mass fraction that you need to match the radii. So those 3 masses, and then shoot for the radii, shoot for the water mass fraction to give that radii. So all the planets along the blue line here have the same mass and radii. You can see down here at low, when you have no core and just mantle, you need very little water for this planet. And then as the core increases, you need more water to make up that higher density core. You need more water to make up that radii to still match that mass and radii that you've measured. So my work is focused right now on TRAPPIST-1F. This is what happens if you take now 5,000 measurements of mass and radii here from AGL 21. TRAPPIST-1F is this amazing 1 Earth radii, 1 Earth mass planet. Taking 5,000 measurements, swinging it across 101 refractory core mass fractions, and then solving for the water mass fraction to match that mass and radii is 5,000 blue lines across here. This is 2.5 million runs of MAGRATHEA. It takes just about 2.5 days on 12 cores, which is relatively short depending on your computer resources. But all the planets here in the blue are possible for TRAPPIST-1F. We have the median here in light blue and the 1 sigmas in dashed lines. And we can pick out some planets on here. So if you're at an Earth-like RCMF, so Earth-like core to mantle ratio, then you would need about 6.5. On average, you would need 6.5% of your weight in water. We can also ask if TRAPPIST-1F is dry, if it has no water at all, then it means it has to have a small core. It means it needs only a 14% core mass fraction. And one fun thing we did, also with that high school student, is we took MAGRATHEA outputs. If we take these 2 planets, solve it through MAGRATHEA, look at the structure file, actually looks at the solution throughout this planet. We put those into Blender. So Blender is a 3D modeling software. And we can take a MAGRATHEA output automatically, putting a shell at each radii and then coloring those shells with the correct color for composition. So these are 3 different possible interiors for TRAPPIST-1F. The side here is kind of that median profile at an Earth-like RCMF. The top is a Mercury-like RCMF, so a massive core needs a massive hydrosphere to match that radii. And the bottom is a dry planet, so it has a very small core. You can't even, the core gets cut off here in the picture. So we can point out those different materials. The iron here is gray. The green is all these mantle rocks. Mantle rocks are made with olivine, so they're green here. The dark green is a post-perovskite phase at high pressure silicates. We've got light silicates on top, while the planet with a massive hydrosphere doesn't have those lighter silicates. Instead, it has that high pressure ice at the bottom of the hydrosphere. So it has ice 10 at the bottom of the hydrosphere. So that's a fun thing we have in a separate GitHub. You can see github.com/davidrwright/blender-magrathea. It's a fun thing to do. And also looks great in papers too. So you might be wondering about bigger planets. TRAPPIST-1F, amazing measurement. We can do bigger planets if you put the right caveats to it. Here in McDonald, Fail, Quinn, and Rice 2022, I found the compositions of K2-138 B through E. That work is focused on finding the resonant, confirms the resonant structure of K2-138, and then uses that resonant structure to confine the masses by just a little bit. So we solve the composition and we find K2-138b can be solved with these 3-layer water mantle core planets, while the outer planets really need an atmosphere to match those masses and radii. So on the right here is a mass percent of water. So we've picked some core to mantle ratio underneath, and then solved across water mass fraction here on the x-axis for the atmosphere mass fraction to match these masses and radii. So you can see C and D here have possibly very similar atmosphere mass fractions, while E requires a much larger atmosphere mass fraction for these planets. And 20 minutes, one more plot for fun is this is the water worlds from Luke and Palais 2022. So Luke and Palais 2022 reanalyzed 9 planets around M-dwarf stars, significantly improving the mass and radius uncertainties. And they found that they kind of lie on these two tentative lines, provocative lines, of one line being a 50-50 water to mantle ratio, and one being a 67 to 33 mantle to core ratio, like the Earth. So an Earth-like line and a water world line. So these are those 9 planets with isocomposition lines from MAGRATHEA, a mass radius line here, along with TRAPPIST-1F. You can see how amazing the uncertainties on TRAPPIST-1F are. And one thing I did with this is we take all of those different mass and radius measurements, do the same thing with TRAPPIST-1F, solve for all the possible 3-layer interior structure for these planets, and then we can summarize those 3-layer interior structures into an uncompressed density. So taking all of those simulated planets that match the mass and radii of these planets and then uncompressing them. So take however much material there are at room temperature and room pressure, what would the density of the planets be? So this is a interesting graph to think about that I probably don't have time to talk about completely here, but we've got uncompressed density on the Y and bulk density on the X. You can see Earth here is at 1 bulk density relative to the Earth, and about 4 uncompressed density, so 4 grams per centimeter cubed. And these planets all lie below that Earth line because they have solutions that could have water on these planets. And they look a little bit different in this parameter space. So we've analyzed the peakiness of these 2 distributions. So that was some graphs that I hope inspired some interest in MAGRATHEA. I'm completely available for collaboration and communication. I can provide some tutorials and some more help. Currently in development with a couple different groups that are using MAGRATHEA is we're finalizing that composition finder and analyzing observed planets. We have a couple of groups analyzing observed planets with the code, expanding that equation of state library, putting in mixtures. So we have a rock ice mix in Alona Fazan's group. And I'm also my current project is working on ideal mixing all throughout the planet. Also putting an entropy function for temperature. So not only isentropic, but you can put in an external entropy function to solve the temperature throughout the planet. Some ideas, MAGRATHEA is great for undergrads, graduate students, your own research. I say you can get an undergrad up to speed on it in just a day, maybe a week for undergrads, but 1 grad student afternoon, you should be up and running with MAGRATHEA. Some ideas is to put a non-ideal atmosphere, 3-dimensional PVT table interpolator has been on the top of the list for a long time that we haven't gotten to. Improved water layer, coupled to atmosphere model, coupled to a thermal evolution model. I've got all kinds of ideas of things that need to be developed for MAGRATHEA. And we encourage the community to contribute, and you can become a MAGRATHEAN here at the link. So thank you for your time and for listening.
Awesome.
Sorry,
thank you. Oh yeah, thank you for your talk. And I think what we'll do now is we're going to turn things over for the questions, and Sam is going to run the questions.
Yeah, sure. So yeah, there are some questions in the chat already, and if you have more questions, feel free to add them to the chat, or you can raise your hand in however you raise your hand, and I can call on you. So the first question is from Michael, and is the EOS in MAGRATHEA something that we could extract to use in a multi-D hydrocode?
Multi-D hydrocode. Yes, I would love to link MAGRATHEA to SPH and crash some planets together. It would be super fun. And yeah, we have a function built in the code where you can make your phase diagram and it'll output the equation of state at some given pressures. It needs updated so you can output it at pressures and temperatures. But right now you can output them at pressures. So we should put that temperature in there too. But we have a built-in function to output equations of state.
Okay, great. Next is from Joe, and he asks, when will MAGRATHEA be integrated into Starfield?
I think you can skip Joe's questions.
You always skip my questions.
I gave a talk on Astronomy on Tap. I started the Astronomy on Tap in Las Vegas, and I had a guy who does virtual reality. Like his whole thing is making virtual reality a thing. So would love to get a website developer and run this through a website too. Would make it a lot easier. That would be fun.
Okay, good to know. Next question is from Avi Mandel and asks, I've heard quite a bit that much of Earth's water is not at the surface, excuse me, and rather dispersed in the core and the mantle. Is this an uncertainty factor for these models, and how is that handled?
Hey, that's a great question, Avi. For the Earth, it's still a very small percentage of water. It still has very small effect on the Earth's interior, affects the temperature gradient some, but we're still talking about way less than 1%, 0.1% of the mass in water. As we have been thinking about mantle hydration, there's a couple works on mantle hydration with interior models out there. Dorn Group has a couple. And it's really exciting. You can pump up the radii by putting some water inside the core, and that's what my postdoc is largely focused on is ideal mixing. So you can mix different equations of state together throughout the whole planet. Really will be this next level of interior models in the future.
Okay, great. Let's see what else this. Okay. Joe's got some good comments. So Michael says he was particularly interested in modeling mantle convection in multi-D.
Yeah, that'd be exciting.
Yeah. Okay. Good deal.
Yeah, all those. Yeah, we've been thinking about thermal evolution. A lot of works with thermal evolution ignore material properties, and that's something we care a lot about in MAGRATHEA. So it'd be great to test out those different materials in those convection codes.